All right, so last time we started section 5.4, which has two different components in it. It has a component about factors, which is what we did last time, called greatest common factors. And then it has this component that we're going to do this time called multiples, least common multiples. And I think this is the slide we're on. Does this look right?
Yes.
Yes. Why are you smiling?
We were just talking about that yesterday, the day before.
Yes, we were. That's right. All right, so last class when we were looking at factors, and we talked a little bit about the relationship between the two things. It was back earlier on. Oh, maybe it was in the last section, actually. I think it was. Back in section 5.1, we defined what multiples and factors are. And I reminded you of the fact that multiples are like your multiplication tables when you learned those back in third grade. Factors is an idea about division. So one's an idea about multiplication, the other's an idea about division. But we're going to do one more issue to talk about, and it's going to come into play when we do multiples, even though it's a feature about factors. And it's the idea of being relatively prime. So two numbers whose greatest common factor is 1 are numbers that are relatively prime. So the point when we had relatively prime numbers before now was the point when we had to stop factoring. They didn't have any more factors in common. We got to a point where they were what we would call relatively prime. And let me flip back one slide. I promise I'll come back. So right over here, for instance, when I got down to this point where I had the 41 and the 36, it's coming up just a sec. There it is. That 41 and that 36. It happens to be true that 41 is a prime number, and it also happens to be true that 36 is not. However, the issue is not whether or not they're prime. The issue is the fact that they don't have anything in common any longer. Okay, so that's what it takes to be relatively prime. They don't have any factors in common any longer.
So those would be relatively prime.
Yes, they would. 41 and 36 would be relatively prime. Now, we need that feature because that kind of tells us where we stop factoring, right? We stop factoring when we are not able to do so anymore. But we have this sort of term, relatively prime. It means they're prime relative to one another, not relative to the prime numbers, but to one another. All right, so the other section here in this then is the least common multiple idea. So a least common multiple of a set of numbers is the smallest natural number that is a multiple of all the numbers in the group. And the confusion comes in with the word least here. Least sounds like it's something that's small, right? I mean, it's the least versus the greatest, right? Greatest common factor sounds like it's something that's large. But remember what the word least is modifying. Okay, so I'm not an English teacher, but I remember a little bit about modification of nouns and whatnot, right? Is that this idea least is related to the idea of the multiples. So if I'm talking about the multiples of 3, multiplication tables of 3 would be 3, 6, 9, 12, 15, 18, 21, and so forth. We keep going, right? Well, all of those numbers are at least as big as the number I started with, 3, aren't they? So if I'm looking for a least common multiple and it's got the 3 in it, then it's going to be at least as big as 3. So even though it is a least common multiple, it's bigger than the values, or at least as big as the values I began with. Are you with me? Whereas when we did greatest common factors, that was the other way around. The word greatest was modifying the idea of being a factor. And the idea of being a factor means that it's a number that divides smaller than it, or at least as small. All right, so enough of that. We're going to take a look at some of these. So there's 3 methods, just like there were 3 methods for greatest common factor, there's 3 methods for least common multiple. So the first one is the prime factors method, and it is just like the prime factors method, or at least the beginning of it. It's just like the prime factors method for finding the greatest common factor. So what you're going to do is you're going to write the factorizations out for the numbers. You're going to choose all of the factors that they have in them at all. Okay, every factor will be in the least common multiples, not just the ones that are in common, but every factor. And then you're going to write them to the highest exponent that's present instead of the lowest exponent that's present. Okay, so this is raising this to the greatest exponent. And then you multiply all those values together, and that gives you a least common multiple. Okay, you ready to try one? Nicole said no. Is anybody ready to try one? I got a few nods. All right, we're going to give it a go. We have three numbers, 90, 50, and 20. And we can use two numbers as easily and as well as three numbers. It doesn't matter, how many numbers we have. The process is the same. What we're going to do is we're going to find their factorization. So least common multiple, greatest common factor, you find factors. Okay. So I'm going to do this with the prime factorization method, which means I find each one of these factor expansions. So what is the smallest number that divides 90? Smallest prime number? 2. 90 divided by 2 is 45. 45, smallest number that divides it. 3 will work. 5 will too, but it's not the smallest. 3 will work. What is 45? How do I know that 45 divides 3? 3 divides 45? Yeah, 4 plus 5 is 9. Yes.
If you forgot or didn't do 3 and you did 5, would that screw you up?
It wouldn't give you the wrong expansion, but it wouldn't give you the expansion in order, which means it wouldn't actually be following this pattern when we discussed this. That is, that it's from smallest to largest.
All you have to do
Is to rewrite the order.
Okay.
Yeah. So if you did 5, for instance, and then you did a 3, and then you did another 5, your two 5s wouldn't be grouped together, so it's just not quite as pretty. I mean, it doesn't kind of concise. It's not as concise.
Okay.
So yeah, but it wouldn't really hurt things. All right. So what is 45 divided by 3? 15. 15 also is divisible by the 3, though, right? And then I end up with the 5, and so the 5's the bottom. How about 50? Smallest number that divides 50? 2. And I get 25. Smallest number that divides 25? 5. And I get 5. Smallest number that divides 20? 2. And I get smallest number that divides 10? 2. And I get 5. All right, so what I want to do next is I'm going to write each one of these out with their factor expansions, because otherwise it's not going to work with the directions that I was given, and it's really easy to either forget an extra value or get an extra value that you don't need. All right, so this is 2 times 3 squared times 5. Are we good with that one? Okay. Now 50 is 2 times 5 squared. And then 20 is 2 squared times 5. None of my other Apple TVs have a delay in them like this. Look, there they are. How fast was that? All right. So here's how you do this. This is the least common multiple, LCM. I take each factor. So what's the smallest factor that's in any of these factor lists? 2, and I write it to the highest exponent. So what is the highest exponent among these lists? Squared. What is the next prime factor? 3. And what is its highest exponent in any list? Squared. It's got 2. What is the next prime factor in any list? 5. And what is its highest exponent? Squared. And there aren't any others. If we had a 7 or a 13 or whatever, we'd include them as well. But there aren't any others. So I've got 2 squared, 3 squared, and 5 squared. And I'm going to multiply them. So you can grab your calculator. And 2 squared is 4, and 3 squared is 9, and 5 squared is 25, of course. So you can multiply 4 times 9 times 25. Does somebody have one? Say it loud. 900. So 900 is the least common multiple. Is that okay?
So that means that's the smallest number that all of them can multiply something by and equal.
Exactly. So 90 would be multiplied by 10 to get 900. 50 would be multiplied by 18. 18 to get 900. And 20 would be multiplied by, what did it? 450? That would be 2. 45? 45, yeah. So 20 would be multiplied by 45 to get 900. But that's the smallest one. No number smaller than that has all three of these as factors. Okay. There's certainly numbers larger than this that do. One number that's larger than this that would work would be 90 times 50 times 20. mean, that is a common multiple. It's just not the least one. So, all right, this is one method. We've got 2 others still to go. So here's your next one. You got lots to write on this slide as soon as it decides to show up on your screen. There we go. All right, so you've seen this description before. That is this dividing by prime factors method description. So what we see described here is you write the numbers in a row. You divide them by a common factor, just like we did before. And the difference is that you don't necessarily stop if you're doing 3 factors. If all 3 of them have nothing in common, as long as 2 of them still have something in common, you keep dividing. Okay, so we're going to do some division with them all in the same row. And then the construction of the least common multiple is, of course, different. What you do is you divide, I'm sorry, we already talked about that. You take the least common multiple as the product of all the divisors and final quotients. Okay, so jot the description down, and then we'll do one. All right, so we're going to try one of these. The numbers we're going to use are 90, 100, and 20. And we write them in a line right next to each other, 90, 100, 20. The order doesn't matter. If I wanted to put them in some other order, that would be fine. And we did this process before, but for a different purpose. Our goal is to look at all of those and find a prime factor that they divide by. So what is a prime number that they all divide by? 2. Sure, why not? Okay, so we've got 2. So 90 divided by 2 is 45. 100 divided by 2 is, and 20 divided by 2 is 10. Okay. Now, I need another number. It doesn't have to be small, as large as anything, but another prime number they all divide by. 5 will work. All right, so 45 divided by 5? 9. 50 divided by 5? And 10 divided by 5? 2. Now, at this point is where we would have had to have stopped if we were finding a greatest common factor. All right? Because there's not a factor common to all 3 of those numbers at the end, correct? 9, 10, and 2. They do not all have a common factor. However, 2 of them do. So we're going to continue the process one more time because this is least common multiple. And we want to know the factor that will divide the 2 that do, in fact, divide. And it's a 2, yeah? So the 9 doesn't change. We just rewrite it. Okay? And then we divide the other 2 that do divide, and we divide them. So 10 divided by 2, 5, and 2 divided by 2, 1. Now, the least common multiple is all the numbers on the side, because they were factors, and all the numbers along the bottom, because they were quotients. So my least common multiple is 2 times 5 times 2 times 9 times 5, and you could say times 1 if you prefer, but this is the least common multiple. 2, 5, 2, 9, 5. All right, so what's 2 times 5? 10 times 2 is 20, so this is 20 times, and then 9 times 5 is 45. So you have to take 20 times 45, and somebody's going to do that for us. It's 900. Still 900 is a different set of numbers than we had on the previous screen, but this least common multiple is still 900. Okay. So we don't have to look for powers on this method, but we have to remember that we do not stop at the 9, 10, 2. If you stop early, what you'll end up getting is a common multiple, but it will not be the least common multiple. If I had stopped early and I had the 2 and the 5 on the side, I would have had the 9, 10, and 2 on the bottom. I would not have gotten 900. I would have gotten 1800, which is a common multiple, but it's not the smallest. Okay? One more method. This is a formula. All right? Least common multiple of m and n can be found by the following. So you take m times n. This is a multiplication dot. And you divide it by the greatest common factor of m and n. So this kind of approach is really nice if you were given 2 or 3 numbers or whatever, and you were asked to find both the greatest common factor and the least common multiple. Make sense? Because, I mean, I don't want to find the greatest common factor if I'm not actually asked to. But if I already have found it, sure, I'd like to use it to make the problem easier to work with after that. Okay? And there's a note at the bottom that makes things a little bit restrictive, but you can only do this if you have 2 values, not if you have more. Okay, so let's take a look at one. And it's one that we've already found the greatest common factor for, back on problem number 3. So we have 72 and 126. And last class, we found the greatest common factor for 72 and 126 from problem number 3. And what did we find that greatest common factor was? 18. Okay, so we're using information we found from last time. Are we all good with that? Okay. So according to this formula, the least common multiple can be found by taking the product of 72 times 126 and dividing it by the the greatest common factor, which was 18. I can't do any of that in my head. So, yeah, I know. All right, so somebody tell me what 72 times 126 is. Just the top for now.
1,072.
1,000, say again, Tyler?
9,072.
One more time.
9,072.
Oh, that's why I didn't hear it. I was listening for hundreds, and there wasn't one, right? Okay. And then you divide that by 18.
504.
504?
Yeah.
So it's definitely the least amount of work because you had the work that you already did on the other problem already done. Okay? All right, we're going to do a couple of slides that have got some true-false questions, I think, if I'm remembering correctly. So let's take a look. Decide whether the statement is true or false. 2 composite numbers may be relatively prime. If it's false, you have to be able to give me an example of 2 that are composite numbers that are also relatively prime to one another. And we had an example, well, at least in the sense that I looked at it and I told you, hey, look at these guys over here in red. 41, 36, one of them was composite, 36, the other one's prime, 41, and those are relatively prime to one another, correct? So it's certainly true that I don't need to have both of them prime for them to be relatively prime. Can you think of 2 numbers that are both composite that are relatively prime to each other? This is false, by the way.
45 and 16.
45 and 16, that'll work. 45 has factors of what? Well, it's divisible by 3 and 9. Of course, 9 is not prime, but 3 and 5, right? 3 and 5 are actually the only prime factors for 45. What's the only prime factor for 16? Say it loud. 2, right? 2 divides 16, and it divides it again, and it divides it again. It divides it 4 times, 2 to the 4th. So this one is actually, if I factored, this one would be 3 squared times 5. This one would be 2 to the 4th. They have no factors in common. And that's what it means to be relatively prime, is that they just have no factors in common. It doesn't actually mean that anything's prime. I know. Great name, huh? All right, 2 natural numbers must have at least one common factor. Any 2 natural numbers, do they have at least one common factor? Yes, that is true. What is the common factor? 1. No matter what 2 numbers I pick, they will at least have one common factor, and that factor is the number 1. Not prime, right? It didn't say prime. They don't have to have a prime factor in common, but they do have a factor in common, which is the factor of 1. Okay, we're going to do one more. If p is a prime number, then the least common multiple of p and p squared is p cubed. And it might help you to think about letting p be a prime number to see if this works. So maybe you say, okay, whoops. You say, okay, well, let's say that p is 5, just so we can talk about it and think about it. If p is 5, what's p squared? 25. And the question is the least common multiple then p cubed, which would be 5 cubed, which would be 125? No. Adam, why not?
There's 25.
Right, the least common multiple of the example that I created would actually be 25, right? 5 times 5 is 25, 25 times 1 is 25. They both have a multiple of 25 if you listed out their multiples. So that's true in general as well for this, because the least common multiple in the actual example would have been p of p and p squared would be p squared, just like a 5 and 5 squared was 5 squared. So this is in fact false. And the key is actually this idea of them being not relatively prime to each other, right? They have a factor in common, so we can't just multiply them together and end up getting their least common multiple. So that's actually related to the idea of being relatively prime. All right, last time